podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to talk about defying gravity. That's possible, right?
No.
No. Okay. So we're going to talk about gravity and how it relates to energy conservation. So I like to write energy conservation as the change in energy equals zero, because
It's just moving from one to the other. Well, I think that the one that I showed in class was the Newton's cradle or a pendulum or something like that. It's funny, I tried to find a Newton's cradle video where it starts swinging, the one starts swinging, and then at the end you don't see it swinging, but all of them are swinging.
Right.
Just a little bit. I tried to find that, I couldn't find that.
And it's a very realistic situation. Yes, the marbles stop, but it's due to friction and some of these other things, forces that that are doing work in steel, the energy.
Right.
And so you guys did this hang time experiment, and actually this ties right into a chapter challenge, where you watched a figure skater jump and you watched a basketball player dunk, and then you guys jumped, and we discussed center of mass and tried to measure the change in position, and et cetera, et cetera. So what I like about energy conservation is that, just like our Feynman explanation last time, you can always find the energy, you just have to know where to look for it. So, for example, if we're talking about your jump, we have the ready, we have the launch, and we have the peak. Now, I would argue that we would have to discuss some other things. We would have to talk about the landing. So, in the ready position, you have only elastic potential energy.
Right, because your muscles are tensed, ready to jump up.
Ready to do work on the ground. Your center of gravity is where it's going to start. It doesn't have a height. Okay, it's at zero position, and you're not moving, so you have zero kinetic energy.
Right.
The moment you launch, this elastic potential energy is completely released, and you have a little gravitational potential energy in that first moment in time that you have left the ground, but your speed is at a maximum, therefore you have maximum kinetic energy. At the top, your muscles still aren't doing anything in terms of this launching, landing, jumping process. You're not moving. We know that at the top, right?
Right.
It's not going up, it's not going down. So that means all of the energy has to be in the form of
Gravitational potential energy. So that's where you're at the max, just like the ball is at the max at the top of the arc.
right. And then what we see here, and I'm gonna relabel this actually. I'm not going to call that max. It is a maximum kinetic energy value, but I'm going to call it a lot. And we'll talk about that in a second. And then when you land, when you're jumping and you land, are your legs straight or do they bend?
They have to bend.
If they don't bend, they'll bend for you.
Blow
actually.
out an E or
yeah,
something.
or worse. And so what will happen here is those muscles will contract, and you have no height, and you're stopping. So what happens here is we can talk about the total energy. Well, max energy at the beginning plus zero is max.
Right.
0 plus a little plus a lot, we've accounted for all of it, so that's our max amount.
Right.
Okay? And we just keep, I can spell. We can just keep writing this out. 0 plus plus 0, max plus 0. We have these maximum amounts. We've accounted for all of the energy in our jumping motion.
Right. So what you're really saying is that you can use these to calculate the others.
Yes.
So if I know the elastic potential energy of the ready, I know what my total is going to be for the others.
That is correct.
Right.
Because it's just converted from one form into another. Energy conservation. You could graph that if you'd really like graphs. I love graphs. So at the beginning, I like to think about things that I can visualize. I can't visualize elastic potential energy. We'll talk about that. But what I can visualize is energy conservation means that the total energy is constant all the time. So I could add up any point on these other three graphs, and they have to add up to be the total.
Correct.
So that's the number side of this. But visually speaking, from a gravitational energy point of view, at first it has no gravitational energy. At the top, that's all it has. And at the bottom, when you land, it's got none. So it's going to look something like that.
Okay.
The kinetic energy, it's got a lot to start.
Right.
It's got none at the top.
Right.
It's got a lot to finish.
Correct.
Okay, so there's that. Now, there's that one moment in time of the launch where it's got a lot and then no elastic the whole time until the very end when the legs recompress and the muscles contract. So at any one moment in time, we can add this up.
Right.
Now, the graph isn't perfect. It's not pretty. But so this is the elastic. And by the way, to get this energy, we have to think about this. To get this energy, we have to realize that we do work on the ground. So you're applying a force over the distance of the knee bend to the legs being straight.
Right.
The more you bend the knees, the higher you can jump theoretically. So what if let's see, we do more work
On the ground.
more work on the ground? Then what?
Well, we should go higher.
Yeah, then we jump higher. Or if we do less work on the ground, then
We won't jump as high.
right. So imagine just jumping with your calves. So you don't bend your knees. You don't get too high off the ground. But if you bend the knees and keep your back straight and stick your butt out and do all those things that you're supposed to do, then you jump significantly higher. If we were to take our table back here and actually put numbers in, what you would see is that all of this has to match up because we are in fact talking about energy conservation, which is actually exactly what you did in the investigation. The book has you do some things where they work through some sample problems. So let's just take a brief look at one of those. It said on page 240, it says a trainer lifts a 5-kilogram equipment bag from the floor to the shelf of a locker. The locker shelf is 1.6 meters off the floor. How much force will be required to lift the bag off the floor? How much work will be done? How much potential energy does the bag have? If the bag falls, how fast will it be going? So this is a great example for us to work on. First question is, well, let me write down my stuff. I got a 5-kilogram mass. Okay. And I know that it's going to sit some height 1.6 meters off the floor.
Right.
I know that gravity is 9.81 meters per second squared.
Right.
And the first part of the question is, how much force? Well, what force do I have to overcome to get this bag from the floor to the shelf? I have to overcome
Gravity.
which is causing the bag to have some weight.
Weight.
Yeah. And so once I overcome the weight of the bag, so 5 times 9.81, I hack my way through this, and the book says
78.4.
no, 49. 5 times 9.81. About
that's right.
49 newtons is what I have to overcome. Yeah, you looked ahead, Mr. Sadler.
Oh,
It was
you were
asking.
just getting mass.
Yeah,
Or
I was
just
getting
weight
weight.
from the
So how much work is done? So how do I find that?
mass. Right, I just have to take that work equals force times distance.
Right. And in this case, the weight force times the height that I'm going to lift it.
Mhm.
And so the 49 times the 1.6, and that is, of course, measured in joules. So 78 joules of work is required to do this. C says, how much potential energy? So I ask questions like, by placing the bag on the shelf, does it have any elastic potential energy? No. by placing the bag on the shelf, have I given it gravitational potential energy?
Yes.
And according to this whole work energy theorem, conservation of energy, if the energy change has to be 0, and it took 78 joules of work to get it there, how much energy does it now have? It has
78.
78 joules, right? So it's got the 78 joules of energy as it sits up there. Now the next part of the question says, how fast will it go?
If I throw it off the shelf?
Yeah, how fast will it go if it falls or if you push it? And so we could reach back into chapter 1 and we could say, hey, well, I know originally it's not moving, and I know how high it's going to fall, and I know the rate of gravity. So I could dig up this equation that doesn't have any time in it, and we're actually going to do that as a sidebar. And I say, well, the final speed is the square root of 2g times the change in y, or the change in height. So just to keep my symbols the same. That's the chapter 1 way. The chapter 2 way is, as it falls, it's losing gravitational energy and gaining
kinetic energy.
And according to energy conservation, if it had 78 joules of gravitational energy, at the bottom it's going to have
78 of kinetic energy, 78 joules of kinetic energy.
And I have this equation for kinetic energy that's half mv squared.
Right.
And so I work my way through this.
I know the kinetic energy, I know the mass, and I should be able to calculate the speed.
So 2 times the kinetic energy divided by the mass, take the root of that. 2 times 78 over 5. The root of that is 5.6 meters per second. Does this work over here? 2 times 9.81 times 1.6. Take the root of that. So let's see, 20 square root of 35. Yeah, I'm pretty close.
Right.
Okay, it's not, and I say it's not perfect. It's perfect. But just some rough math in my head tells me that either way works.
6 times 6 would be 36, so it has to be.
But we're close.
Right.
All right, so that when they say they get 31 here, this is 2 times 9.81 is obviously less than 20. So I embellished a little bit, but we do get to the right answer, which is nice to see. And so many ways to solve one problem. So I believe that covers energy conservation. We see the connection between work and the different types of energies and jumping, etc. So signing off, this is Mr. White.
And Mr. Sadler.